So our second example, the fx is equals to x times L minus x. And this is continuous function, quadratic function. It's not constant anymore. And when x equals to 0, f0 equals to 0. When x equals to L, fL equals to 0. So it's satisfied for the boundary conditions for the Sturm-Liouville problem, which is minus y double prime equals to 4y. The y naught equals to 0, yL equals to 0. So the boundary conditions for the continuous function satisfy for the homogeneous boundary conditions for the Sturm-Liouville problem. And we use the generalized Fourier series expansion to represent our fx. We solve as fx equals to 8L cubed divided by, L squared divided by pi cubed. Sum from n equals to 1 to infinity, where 1 over n cubed sine n pi x over L, where n is only the odd number, 1, 3, 5 until infinity. And now we are trying to code these equations into the MATLAB and trying to compare our fx using generalized Fourier series expansion to represent this continuous fx and compare to the original fx, whether they are fitting to each other or not. Okay, so let's see the MATLAB. Okay, this is the script to use Fourier series to represent fx equals to x times L minus x. The goal here is trying to evaluate the infinite series expansion for fx equals to x times L minus x in terms of sine and cosine format, basically sine format here for the Fourier series expansion. The coefficient as we derive is 8 times L squared divided by pi cube m cube, where this m is only the odd number here. And the orthogonal basis site is the sine n pi x over L, as we derive from the Sturm-Liouville problem site, where the m is only the odd number. That's why we said m equals to 2n minus 1, where n is the integer. From 1 to infinity, m is only the odd number from 1 to infinity. And as per usual, we can clear out, close out for all the script we ran before. We set up the domain of our variable x, independent variable x. X should be from 0 to L. As we derived domain L equals to 3 previously, we define L equals to 3 here as well. We set up 200 dots in between 0 to L for the x. And we define our coefficients for the sum part, which is 8 times L squared divided by pi cube. Our exact function is now constant anymore. It's a quadratic function, x times L minus x. Since my x is vector format, so when you do the times L minus x, should be a dot time here. Well, we will calculate the Fourier series approximation to represent our continuous function. This is very similar to how we code for the power series. So we set up basically the sum of our Fourier series, and we put zeros at the beginning. Of course, we will set up a maximum iteration number, which is 50 here, because previously we code our fx equals 1, that maximum iteration we use is 50, so we set up 50 here. We set up the tolerance so that if the sum of s step is making very small change of the whole sum, then we will stop for our while loop. But if the significant change happen when we add the sum of the S term, then we will still going around this looping. Of course, we need to set up an initial arrow, which should be bigger than the tolerance so that we can start our while loop. We set up an initial iteration, which has to be smaller than the maximum so that we can start the looping. We set up the while loop and we set up two conditions. When my arrow is bigger than the tolerance, or when the step we are running is smaller than the maximum iteration, the while loop will still run. However, if one of the conditions satisfied, for example, if the relatively change of the S terms on the sum is smaller than the tolerance, or the S term looping is bigger than the maximum looping you want to run, then it will stop. Well, when we define the iteration loop, we will define our M, which should be a odd term. So the M is always equals to 2n minus 1. And we can write that at S term, what is the Fourier series expansion for that term, which is the coefficient divided by the m cubed times sine m pi x over L. That is what we derive from the analytical solutions. Then we will update our sum always. So the sum has already defined as 0. Then as we running more and more loops, we will have all the term added to the sum. So FA will be always updated with the new term FF. And we will trying to find, okay, because this FX is vector format, so that inside this vector for all the x you are running, inside this vector, whenever the relatively S term is bigger than it, making a relatively change of the sum is bigger than the tolerance, we will stop this looping. But if that relatively change is smaller than the tolerance, we will still doing this loop. In the end, you will plot you will plot basically the x and FE, which is the exact solution, as well as the x of FA, which is the sum of your general Fourier series. And you can compare them, trying to see using general Fourier series expansion to represent your continuous function, how that can be differentiated with your exact solution. And let's just run it. After run, you will get a picture. So this picture is basically the exact function vs the approximate function, where this approximate function is expanded by Fourier series. And you can see they are perfectly overlapping, as well as the boundary conditions. So the only difference is for this one, the continuous function satisfy for the boundary conditions. So you didn't see that noisy at the boundary condition, which x equals to 0 and x equals to 3, where you see that noisy before, because that continuous function fx equals to 1 didn't satisfy for the boundary conditions of the Sturm-Liouville problem side. So you can see that when you have a continuous function where satisfy the boundary conditions of the Sturm-Liouville problem, you can use the orthogonal basis site to represent uniquely of your continuous function, which is the general Fourier series approximation. Okay.